This here is a half-wave microwave dipole antenna. That was a lot of words. So let's clarify what those mean. You can see there are two pieces of metal sticking up and down. One's connected to the ground, one's connected to the voltage. Together they carry the signal, positive and negative. Now when we send an AC signal to it, which side is positive and which side is negative alternate. So it goes positive, negative, negative, positive, and back and forth. Now, being an AC signal, it looks sort of like a sine wave, where we go from our maximum to our minimum, or our minimum to our maximum. Now you'll notice that from the max to the min is about half the overall length, and the same from the min to the max. So, if this side is positive and this side is negative, maximum, minimum, it only takes up about a half of a wavelength. So that's the half wave portion. Now if the top and bottom have opposite charges, we're approximating an electric dipole. So there's the dipole part. Now this length here is about 6.4 centimeters. Now being a half wave, double that, we get about 12.8 centimeters, which is the wavelength of microwaves. This little electric dipole creates an electrostatic field. And if I flip the voltage, it creates the opposite electrostatic field. But that field doesn't change instantly. If I flip the voltage here, it'll take a few nanoseconds for the electric field over here to notice. Specifically, those changes propagate at the speed of light. It would take light about 3 nanoseconds to get this far from here. So if I change the voltage here, the electric field here won't change until 3 nanoseconds later. Now what if I start oscillating this faster than 3 nanoseconds? The electric field here is already going to be changing again before the change even registers over here. And the faster those changes go, the tighter that electric dipole field is. And eventually, that tightening will have a wavelength corresponding to these conductors. And that occurs at microwave frequencies. In this case, about 2.5 gigahertz. Because if you multiply a microwave frequency by a microwave wavelength, you get the speed of light. And we have electromagnetic radiation, which is what makes this an antenna. So we're going to send a microwave signal through this antenna and pick it up with this receiver. And the easiest way for us to detect that signal is by piggybacking another signal onto it, using amplitude modulation. Amplitude modulation is what happens when we multiply two signals together. Two sine waves with different frequencies. So visually, we might have a very fast wave that we modulate with a very slow wave. And the result is the product of them. We can transmit information this way. For example, audio signals. Audio signals are on the order of 20 kilohertz at most. Picking up a 20 kilohertz signal with an antenna is no easy task. But picking up microwaves with an antenna, or even radio frequencies, something in the megahertz to gigahertz range, is a lot easier. So we can piggyback our slow audio signal onto our fast radio signal. The wavelength of a few kilohertz signals is pretty large. But once we start talking about megahertz and gigahertz, we're talking about antennae that are less than a meter long. Those ones are more convenient. Because this combined signal has a fast frequency, it can be picked up by a small antenna. Then all we have to do is use a low-pass filter to filter out all the very high frequencies, and we get our audio signal. Now obviously, since radiation spreads, the signal is going to be stronger the closer I get to our source. Some AC/DC always feels appropriate for electrical experiments. Now since this is an AC signal, I can flip my receiver over and I should get the same input. Now since this is a dipole antenna and it's oscillating up and down, no matter what frequency I'm at, the electric field in the horizontal plane is always zero. So I won't be able to pick up a signal like this. The wave is polarized. And again, we get our best signal when the frequency matches the wavelength. If I lower the frequency to, say, 1.5 gigahertz, I can still pick it up, but it's not as strong. And as I raise the frequency up to match this wavelength and then past it, you'll notice the signal peaks and then dies out again. It's almost like turning up and down the volume. Now I have two outputting antennae. They'll be generating the same signal. We'll unfortunately have to use a pure 400 Hz audio signal for this, A, for copyright reasons, and B, because we want to note precisely where audio gets louder and softer. Now, if you have a wave traveling in one direction and an identical wave traveling in the opposite direction, they'll create standing waves. For us, that means that the amplitude of the oscillation is going to vary periodically with distance in between these two, which has been helpfully marked on this ruler here, each stripe being an additional half wavelength. Now we move it over a quarter wavelength, and the signal goes away. Another quarter wavelength, and it comes back. Gone, back, gone, back. Now, since it's only the amplitude that varies with distance, that means at each location, it's an AC signal, positive and negative. So I can turn this upside down and get the same signal. And I still have no signal if I'm sideways. I can change where those standing wave nodes are if I turn one of my radiating antennae upside down. I have here a little microwave resonance chamber. As you can see by its size, it's about the scale of microwaves. Now, thanks to its internal geometry and various boundary conditions, microwaves of various frequencies can form standing waves in here. In practical terms to us, that means that certain frequencies will get much larger amplitudes coming out of here. So we're going to look at the resonant frequencies of this chamber. As before, you'll be able to hear them because we're sending an AM signal with a 400 Hz audio tone on it. So we found especially large peaks around 3270, 3518, and 3830 megahertz. Now we'll see if we can disrupt that resonance by introducing a new boundary condition. By adding a new conductor in the middle, we disrupt the microwave field.